Let's talk about vaporization, the process in which something goes from a liquid to a gas. So that's what vaporization is. Condensation is the opposite. It's a transition from a gas state into a liquid state. So here we have an illustration of a beaker of water. And we have our little water molecules in here. And I forget who this quote is from. I should probably put it on there. But if you look at the molecular level, a famous scientist said it's a wild dance floor there at the molecular level. So I think of like a mosh pit or something. Just, people just, all over the place. Just touchingly close, and it's not something I would be interested in, but I know it happens. So just moving around, right? So these particles are moving. They have an average energy, average kinetic energy, which is related to their temperature, right? But in an average situation, you have some that are high and some that are low, right? So if you have a particle here with high energy and it gets to the surface, it can actually escape and break loose and go off into the gas state. What do gas particles do? How do they travel? Random? Sort of. Their direction will be random, but they're going to go in a straight line until they bump into something, right? Because why would they, they can't steer. They're not going in spirals or anything. They're just going to go in a straight line off wherever they got shot, straight line until they bump into something, then they're going to ricochet off and go in some other straight line. So we've got water molecules escaping, and then like this one and this one coming from the air, they're on a crash course for the surface of the water. What's going to happen when they hit the surface? They're going to get stuck, right? Because here they're hitting liquid water. They are water. There are strong attractive forces here. They're not going to bounce off the surface of the water. They're going to stick. Now, they might be able to escape again later, but they're going to stick at least for the time being. I think of what's going on here a little bit like a game of Red Rover. Have you guys played Red Rover? They don't let kids play that anymore because you could break an arm. You can break an arm walking down the sidewalk too, but they haven't outlawed that. Anyway, for those of you who haven't played Red Rover, you've got two groups of children out on the playground, and they make two lines on opposite sides of the grassy field, and they hold hands, parallel lines. And then someone from one line says, Red Rover, send Sally right over. I always pick on Sally because I haven't met a Sally in my class yet. So Sally comes running across the field, and she's trying to break through your hands, right? She's trying to break through the line. Well, she's not going to run at a person because it's hard to get through a body, right? But you run right at where the hands are being held, and if the grip isn't very strong, you can get through, right? So how successful Sally is going to depend on how fast she's running, how big she is, and how strong the people are that she chose to run at, right? So if you're playing, with your classmates, you know that, okay, those guys are kind of strong, and those people are weak. And so you aim for the weak people, right? Or you could think about kindergartners and, say, the O-line for the Fresno City football team, right? If you're playing with these guys, it's going to be harder to get through the football players' line, right? Because their grips are stronger. If you're going to be successful there, you better have a lot of momentum, a lot of kinetic energy. You're going to have to run really, really fast. If you're trying to get through these little kindergartners, oh, they're so cute, right, and little, 5 years old, right? To get through those as an adult-sized person, you probably don't even have to run because you have enough mass that you can just push your way through, right? But a small child going at that is going to have to run faster, okay? So how strong the intermolecular forces are has to do with how strong the people are who are holding hands in the Red Rover line. The stronger the people holding hands, the harder it is to get through, right? And in order to get through, you're going to have to run faster. So the speed of the person running has to do with the temperature of the substance. So here's a graph. Scientists really like graphs. So this graph is fraction of molecules having a particular energy versus the amount of kinetic energy. So at a low temperature, blue, because blue is colder, right? We've got this curve. And so there's an average kinetic energy, but only some of the particles actually have the average kinetic energy. Most of them are either above or below. And as you go to higher kinetic energy, it really trails off. So if we say that this dotted line here is the minimum kinetic energy needed to escape. So think about Red Rover. You need to be running this fast in order to break through that line. So the area under this blue curve, those are the particles that have enough energy to break free. If you're running faster, you're going to get through just fine. If you're running slower, you're just going to get stopped, and you're going to be staying. If we heat this up, this curve shifts. The average kinetic energy increases at a higher temperature. It also spreads out. And so we see this tail up here at higher energies spreading out even more. And again, the molecules that have enough energy are the ones in this region under the curve. So at a higher temperature, more of the molecules have enough kinetic energy to break through the line. Does that make sense? So how fast something evaporates or vaporizes depends on the temperature and on the intermolecular forces present in that substance. So to escape, a molecule has to have enough kinetic energy to break free from the intermolecular forces that are holding it together. It also has to get to the surface. It can't break loose if it's just in the middle, right? Where's it going to go? It has to get to the surface. So to increase the rate of evaporation, you can heat the liquid. This is why when you have wet clothing, you put them in the dryer, and the dryer heats them, right? Because they dry faster when it's warm. We know this. Increasing the surface area will also increase the rate of evaporation, because the molecules escaping have to be at the surface. If there's greater surface area, more molecules have that opportunity to escape. So you can think about this. And if you have 2 glasses of water, just room temperature, and you leave one sitting on the counter, and you spill the other one on the counter, it just, it spreads out, right? Which has more surface area, the water in the cup or the water spread out on the counter? The water spread out on the counter. Come back the next morning, which one's more likely to have completely dried up? The one that's spread out, right? It had more surface area. It's going to evaporate more quickly. If you've got something in a cup where it has a small surface area, it's going to take longer for it to evaporate. This is one of the reasons why you go to the public restroom and they have those annoying hand dryers instead of paper towels, right? And if it's working correctly, it should be blowing warm air at you, which helps to speed up the evaporation. And it also, the instructions tell you to rub your hands together. And that's going to help increase the surface area of the water on your hands. Personally, I find that I do not have enough patience to completely dry my hands that way. It just takes way too long. That's why there's toilet seat covers. I wondered what those were for. They're for drying your hands when there aren't any paper towels. My kids would say that's what your jeans are for. Of course, they wouldn't probably bother with the water in the first place. I didn't say that. Okay, so we have mentioned volatile liquids before. We did an experiment where we measured or determined the molar mass of a volatile liquid. A volatile liquid is something that will vaporize easily. Non-volatile means it does not vaporize easily. Those are just relative terms. So can you think of a volatile liquid that you might run into in everyday life? Alcohol. You go to get an immunization and they wipe your skin with alcohol that sterilizes, and it evaporates just right away. Can you think of a non-volatile liquid? Milk? Milk is probably roughly the same as water, maybe a little less because it's got all that stuff in it. So it's oil, yeah. So, I wouldn't recommend doing this with a cup of oil, but you put some oil on the countertop, maybe just a drop of it. And you come back the next day. What happens? It's still there. You wait an awfully long time. I think like vegetable oil would eventually evaporate, but it's going to take like a really, really, really long time. The ants are going to come and eat it first.
And bacon grease.
Bacon grease, yeah. And bacon grease has so many, its intermolecular forces are stronger, so at normal room temperature, it's going to be a solid. Yeah. So volatile and non-volatile. Water is not usually considered a volatile liquid. It doesn't vaporize as easily as a lot of other things that other solvents that we use in chemistry. So there's energy involved in vaporization and condensation. So let's think about that beaker again, but now we're going to imagine that it's thermally insulated from its surroundings. What is going to happen as the water in the beaker evaporates? What happens to the temperature? We have three choices. It stays the same, it goes down, it goes up. Well, what kind of particles are leaving as it evaporates? The high energy ones or the low energy ones? The high energy ones. The high energy particles are leaving. So what does that do to the average kinetic energy of what's left? It causes it to decrease. Lower kinetic energy is lower temperature. If the beaker of water is not able to bring energy in from its surroundings, the temperature of the water will go down as the water evaporates. So vaporization is an endothermic process. This is why swamp coolers work. As the water evaporates, it cools. This is why sweating works. It's why your body sweats. Your body sweats, puts perspiration on your skin. As the perspiration evaporates, it takes heat energy with it and it cools you down because it's the higher energy particles that leave and the lower energy particles are left behind. So vaporization is endothermic. A better way to remember this, though, is to think of, well, how would I make water evaporate faster? Would I heat it up or cool it down? I'd heat it up, right? That's why you put the towel in the dryer. So if I put energy into it, it happens faster. That must be an endothermic process. The opposite, condensation, then, is an exothermic process. This is one that's not as intuitive. When a gas condenses into a liquid, it releases heat. It's not something we really encounter all that much. But if you've ever passed your hand over a pot of boiling water, you know that it's like, it feels crazy hot, right? The reason is that as you pass your hand over there, the gas molecules, the steam, condenses on your hand, and as it condenses, it releases a lot of energy. And that can cause very significant burns. Those steam burns, really, really bad. So the condensation evaporization actually moderates our climate. So I made this graph, just some numbers I got off the internet. So average daily temperatures in July from 1971 to 2000 in Fresno and San Francisco. So the average high in Fresno, 96.6. The average high in San Francisco, 68.2. A lot lower. And it's not that San Francisco is closer to the North Pole, right? It's just mostly east of us, only a little bit north. So that's not the explanation. It's just cooler there. The low temperature here, 66. The low temperature in San Francisco, 54. What's really remarkable is the difference. So in Fresno in July, the temperature, on average, fluctuates 30 degrees within the course of a day. In the San Francisco area, it's more like 14 degrees. That's a big difference. The temperatures here swing wildly. We've had days where it's 40 or even more. 60 degrees, coldest part of the night, and then it's 100 degrees in the afternoon. It's crazy. That's why we never know what to wear, right? Because no matter how you dress, you're going to be uncomfortable for part of the day. So layers are really good. Why does this happen? San Francisco is on a peninsula. It's surrounded by water. Has the ocean on the west and the San Francisco Bay on the north and the east. As the sun shines down, it has energy. That light energy warms the ground, warms the water, warms your skin, warms everything up, right? So all of that water absorbs that energy. It doesn't get as hot because as the water heats up, it can evaporate, and that uses up some of that energy. Then when the sun goes down, and that source of energy is gone, here in the valley where we don't have a lot of moisture, the temperature begins to fall dramatically. And we all wait for that, 6:30 when the sun goes down beyond the trees, and we're like, oh, finally, it's going to cool off now. In San Francisco, it just doesn't cool off that much, but it was never hot to start with, so you don't really care. Why doesn't it get as cold at night? Because you've got the water all around, right? The air temperature cools down, water in the atmosphere condenses, and that releases energy. And you've also got this vast reservoir, of water. Water has a very high specific heat capacity. So it takes a lot of energy to heat it up, and it releases a lot of energy as it cools down. That comes later. So, of course, we can quantify all of that. The heat of vaporization, it's actually the enthalpy of vaporization. Delta H, VAP for vaporization. It's the amount of energy, heat energy needed to vaporize 1 mole of liquid at its normal boiling point. It's per mole because that's just more convenient. So liquid water to water in the gas state requires energy. It's an endothermic process, so we've got a positive delta H here, 40.7 kilojoules per mole. You do not need to memorize those numbers. Heat of vaporization is somewhat temperature dependent, but not super much. That was a bad sentence. Not very much. So here at the normal boiling point of water, 100 degrees Celsius, the heat of vaporization is 40.7. At room temperature, it's 44. It's a little bit higher. And then also listed here are heats of vaporization for 3 different liquids: isopropyl alcohol, acetone, and diethyl ether. Again, at a lower temperature, the heat of vaporization is a little bit higher. So if you need to do calculations, you would be provided either with this information or a table like this where you could look it up. And so you find the heat of vaporization that matches the temperature you're given, and you use that one. When substances condense, the same amount of heat is involved. It's just the direction of flow is different. It'd be really awesome if we could create energy just by evaporating, condensing stuff, but you can't do that, right? Law of conservation of energy. So if it required 40.7 kilojoules to vaporize it, it's going to release 40.7 kilojoules when it condenses. So exactly the same number, different sign, because the energy is going in a different direction. These heats of vaporization make awesome conversion factors between amount of energy and moles of substance. So we can do things like this. Calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. So we're going to need the heat of vaporization. So we go back to this table. We're talking about water at its boiling point So the number we're dealing with here is 40.7. So heat of vaporization is 40.7 kilojoules per mole. This ends up being a conversion problem, unit conversions. So we're starting with 2.58 kilograms of water. And what are we trying to find? Calculate the amount of heat in, wake up, kilojoules, thank you. So we have to figure out how to get from kilograms to kilojoules. Well, the conversion factor is the heat of vaporization. What are the units on that? Kilojoules per mole, right? So that tells us we need moles of water. If we had moles, we could convert to kilojoules. It's always an interesting mix of students. We've got the ones that are like, just can see it, and then the ones who are like, what the heck are we talking about? I have sympathy for both of you, or both kinds of you. So moles to kilojoules. How do we get from kilograms to moles? We're going to go to grams in the middle, right? So we'll go from kilograms to grams and grams to moles. Grams to moles, that's our old friend molar mass. This conversion is the heat of vaporization. And kilograms to grams is just metric kilo prefix stuff, right? So 2.58 kilograms. I've got 3 arrows, so I'm going to have 3 lines. I'm going kilograms to grams to moles to kilojoules. This dimensional analysis stuff does not go away. Put kilograms down here so the units work out. Put grams down here to cancel that unit. Moles down here to cancel this unit. Now we need to stick the numbers in. The units tell us where to put the numbers. So we've got this guy, 40.7 kilojoules per mole. It's 40.7 kilojoules. So over here I've got kilojoules and moles. So the 40.7 goes on the top, and on the bottom is 1 mole. What's the relationship between moles and grams for water? It's 18 now. So you calculate that. I've done it so many times I couldn't forget it if I wanted to. It's 18.016 grams is 1 mole of water. And then the conversion between grams and kilograms, we need to use the meaning of kilo. Kilo is 10 to the 3. So I've got kilo on the bottom. I'm going to put its meaning on the top, 10 to the 3rd grams. So 1 times 10 to the 3rd grams is equal to 1 kilogram. I still have people doing that backwards. So now we just get out our little calculators. 2.58 times 1 EE3 divided by 18.016 times 40.7 equals. Calculator's giving me 5738.12167. Bunch of numbers. How many significant figures should we have? 3. The mass had 3 sig figs, and the heat of vaporization had 3 sig figs. These heats of vaporization are measured. They are not exact. So we should have 3. I'm going to underline the 3rd significant figure. We do not round 5,000 something to 500. So if we're going to stop at this underlined digit, we look at the next one, the decider, and that tells us we have to round this 3 up to a 4. but then we have to replace that with a 0 so that we don't change the value of the number. Or put it in scientific notation, and then you won't have to worry about it. Any questions? How much energy would be released if we condensed 2.58 kilograms of water? The same amount. Just coming in or going out. Which direction? Again, it's like the money, right? Money coming in, money going out. Well, it's positive to one party and it's negative to the other. Just depends on whether you're the one buying or selling. So what happens if you've got vaporization in a sealed container? So here we've got an Erlenmeyer flask with a rubber stopper in it. So here we've got the water. The water is going to begin vaporizing or evaporating, right? Because some of these molecules, even at a low temperature, are going to have enough energy to get into the gas state. Now those particles get into the gas state, they bounce around, they cannot escape, so eventually they're going to hit the surface again, condensation. So at the beginning, we have only evaporation. As we get more and more gas particles here, we get more and more condensation, right? Because in order for condensation to occur, you have to have some gas molecules. The more gas molecules you have, the more that will collide with the surface and condense in any given period of time. So as evaporation continues, we get more and more gas molecules, the rate of condensation increases. At some point, the rate of condensation and the rate of evaporation will be equal. The rate of evaporation depends on the temperature of the substance and on the surface area. We're not changing the temperature here. This is in contact with the room. If it cools down, it's going to absorb energy from the surroundings. If it heats up, it's going to release energy from the surroundings. We can assume that the temperature here is relatively constant. So the rate of evaporation is going to be the same because the surface area is not changing. The rate of condensation, though, depends on the number of particles in the gas state. And so the more particles in the gas state, the higher the rate of condensation. When you get to this point where the rates are equal, that's a situation called a dynamic equilibrium. At this point, you're going to have the same number or same concentration of gas molecules over time. But it's not the same molecules because molecules are continuously evaporating and condensing. And that's why it's dynamic, it's changing. It's a little bit like a busy freeway, you know, and you've got people going south and you've got people going north. And you've got roughly the same number of people at each end of the freeway. They're just, for whatever reason, they want to be on the other end of the freeway. I like the analogy of an airport, busy airport in the middle of the day. You've got flights coming in, you've got flights leaving, right? Is it the same people in the airport all day long? No, it's constantly changing. But if you looked at the number of people, it's probably roughly the same number of people in the airport at any given time. People are coming in airplanes, they're leaving in cars, they're leaving in airplanes, they're coming in cars. Arrivals and departures are roughly equal. Any questions? So if we have water in the gas state here, is that water going to exert a pressure on the container? Yeah, because that's what gases do. So this is going to exert a pressure. We call that the vapor pressure of water. Any closed container of water, well, this one isn't completely sealed, but, you know, get the idea. Here's my soda. And the water evaporates, and there's some water in the gas state above the liquid. And it's going to exert a particular pressure, the vapor pressure. Here we have a graph showing rate increasing up as a function of time. So the rate of evaporation of the liquid into that headspace is going to be constant because the temperature isn't changing and the surface area isn't changing. It's evaporating. The rate of condensation starts out 0 because there was no gas to condense at the beginning. As evaporation proceeds, the amount of gas increases, and so the rate of condensation increases until we get to a point where they're equal. The rate of evaporation is still just chugging along at the same pace, and so we can't increase the rate of condensation anymore because the number of particles in the gas state becomes constant. And that's going to give us a vapor pressure. So vapor pressure is the pressure of a gas in dynamic equilibrium with its liquid. That vapor pressure is going to depend on the intermolecular forces. Because how does rate of evaporation depend on strength of intermolecular forces? If the intermolecular forces are strong, will that make the rate of evaporation higher or lower? Lower. Because you're going, at any given temperature, you're going to have fewer particles that have enough energy to break free. That red rover line is very strong. Fewer people can get through. If the intermolecular forces are very weak, like the little kindergartners, it doesn't take much to get through, and almost anybody can get through. It will evaporate very, very quickly. So if you have low, weak intermolecular forces, the vapor pressure will be higher than if you have strong intermolecular forces. Does that make sense? Have you heard about Le Chateliers Principle? You should have in your previous chemistry class, but maybe you repressed that information. I don't know. Le Chateliers Principle says that when a system in dynamic equilibrium is disturbed, the system will shift, the equilibrium will shift to minimize that disturbance. I can really relate to Le Chateliers Principle because I do not like change. I don't like new things. And so if someone tries to impose a change on me, I resist it, sometimes very strongly. I've become more and more aware of this tendency, much to the annoyance of my husband. I don't like new things. So here you've got a dynamic equilibrium. That looks like it's maybe pentane or something. It evaporates, and so you've got evaporation and condensation, and they've reached an equilibrium, and everything's nice and balanced, and we're all happy and good. So then somebody pulls the plunger up and increases the space. Now, the volume of the liquid isn't going to change, but now the volume that the gas has to occupy is suddenly much larger. So now these gas particles have a lot more space to bounce around in. In essence, their concentration has been decreased. Because we don't normally talk about a concentration of a gas, but how many gas particles in a given volume? That's a concentration. Now the volume's larger, the concentration's less, so these guys are going to bounce around more before they hit the surface. So the rate of condensation is going to go down. The rate of evaporation just keeps chugging along. Because this rate of condensation then is lower, it's going to continue to increase the concentration here in the gas state until it gets equal again. So you increase the volume, and it's going to shift to compensate for that. It's like, oh, well, you're making my volume bigger. Well, I'm going to give you more gas molecules and fill it up just the same way as it was before. If you push down on the plunger and decrease that volume, now the concentration here is too high. And so you're going to have more condensation than you have evaporation, and that's going to continue until the rates are equal again. The vapor pressure is going to be the same after it responds to the disturbance. Any questions? Vapor pressure depends on temperature. So we increase the temperature of a liquid. That increases the rate of evaporation. It doesn't do anything to the rate of condensation, but it does increase the rate of evaporation. Because now more particles have enough energy to get through. So evaporation is higher, That's going to give us more particles in the gas state. It's going to give us a higher vapor pressure. So we can have a small change in temperature giving us a large change in vapor pressure. So here's a graph showing several different substances, the vapor pressure measured in torr versus temperature in degrees Celsius. So here we see the curve for water. Down at 20, 25 degrees Celsius, the vapor pressure of water is really, really small. As we increase the temperature, it goes up quite steeply. And when we get to 100 degrees Celsius, the vapor pressure is equal to atmospheric pressure. Diethyl ether also increases that way, ethyl alcohol. Their curves are all curves, but they have slightly different shapes. The vapor pressure of water depends only on the temperature. Ethylene glycol, that's in radiator fluid, antifreeze. That has a much lower vapor pressure, and so it does not evaporate well. And if you put like oil or something in here, you'd see it at a very, very low vapor pressure, even at high temperatures. So what happens when the water boils? This is the boiling point of water, right? When you heat it to 100 degrees Celsius, now you've got these big bubbles forming. What's going on there? The boiling point is the temperature at which the liquid's vapor pressure is equal to the external pressure. So at this temperature, molecules even in the interior of the liquid have enough energy to escape into the gas state. And so they'll actually make pockets of gas, bubbles of gas, inside the liquid. Those bubbles then, of course, are much less dense than the water around, and so they come to the surface and the water escapes that way. So the normal boiling point of a liquid is the temperature at which its vapor pressure equals 1 atmosphere. For water, that's 100 degrees Celsius. We can actually change the boiling point of a substance by changing its external pressure. You know what a pressure cooker is? So a pressure cooker allows you to cook your food faster. It's got a lid that clamps on, and it's got some sort of a pressure gauge to let you know that, hey, stupid, turn it down because you're going to blow it up here pretty soon. I've never had a pressure cooker, partly because I think my children would play with it. But how does it cook your food faster? Well, water boils at 100 degrees. If you heat it longer in an open pan, it's still 100 degrees. You can't make water, liquid water, get hotter than 100 degrees at atmospheric pressure. If you increase the pressure above the liquid, though, then you have to increase the temperature of the liquid before it boils. So a pressure cooker allows you to cook food in water at higher temperatures, and that's why it cooks faster. That's why frying things is faster than boiling, because oil you can heat to much higher than 100 degrees Celsius, and so the food cooks faster. Of course, there's other problems with frying foods. So this is what we call a heating curve. So temperature in degrees Celsius, and we're adding heat. So we take this water, it's at a cool room temperature, 20 degrees. We add heat to it. We stick this pot on the stove, and we turn the burner on. We're adding heat, we're adding heat. The temperature increases. We're like, oh, this makes sense. You put more heat in, it gets hotter. When it gets to this point, the water begins to boil. When the water is boiling, it's going into the gas state, and those gas molecules are escaping, and those are the high energy molecules. The heat that you're putting in is all going into that vaporization, and then those particles leave, so the temperature remains constant. Because all the heat that you're putting in goes away, and so it just stays the same until you vaporize all of the water molecules. If you boil that pot dry, then the temperature goes up pretty fast after that, because there's no water to take the heat away anymore. Once all the water is in the gas state, you can increase the temperature of the steam by adding more heat. But while there's water present, you can't go above 100 degrees Celsius. This is something that's just not intuitively obvious in our everyday lives. So if you're making spaghetti, as soon as it starts to boil, you might as well put the spaghetti in there. There's no advantage to waiting longer. It's not going to get any hotter. It's just going to stay the same. Any question? So we look at these curves, and that relationship between vapor pressure and temperature is not linear, is it? Those are not straight lines. We like straight lines, so we try to figure out how can we make that into a straight line. It's an exponential relationship. So the vapor pressure is equal to a constant beta Yeah, I need to fix that. That's supposed to be E raised to this power. Let's see if I can doctor this up. So it's E raised to this power. Don't know what happened there. We can rearrange this, taking the natural log of both sides, and then we get the natural log of the vapor pressure is equal to negative H VAP over R times 1 over T. So basically this part plus the natural log of beta. It is not important that you know how to rearrange the equation. It'd be great if everybody could get that, but I'm not going to make you do that. When we rearrange it this way, now we have this in the form of a line. So this is the Y equals, here's M, X plus B. So natural log of beta is going to be the intercept, the y-intercept. X is 1 over T. This is the slope, and Y is the natural log of the vapor pressure. So if we graph the natural log of vapor pressure versus 1 over T, we get a straight line, and that straight line has a slope negative delta H over R. R is the gas constant. So we can determine heat of vaporization experimentally by measuring vapor pressure of the liquid at different temperatures and using a graph. So here's natural log of P and 1 over T. You have to be careful with your units here so that they work out and give you something reasonable. So here we've got millimeters of mercury for this, and we've got kelvins for our temperature. We get a graph like this. So the slope is negative 3,478 Kelvin. That's equal to negative delta H over R. We're going to use this delta H, we're going to use this R, 8.314 joules per mole Kelvin. And so we can solve this and find out that the heat of vaporization here is 28.92 times 10 to the third joules per mole. This is one of those problems that scientists solve. It's like, okay, we want to find out what the heat of vaporization is. It's something that's hard to measure. You can't just get out a ruler and measure it. You can measure vapor pressure, you can measure temperature, and if you know the relationship and can find a way to graph it so that it's linear, then you can figure it out in this way. So the vapor pressure of carbon tetrachloride is measured as a function of the temperature. The results are tabulated to determine the heat of vaporization of carbon tetrachloride. This is a really hard one to do on a PowerPoint slide. Is what do we need to do? We need to graph the data and find the linear regression line and find the slope of the line. But we're not going to graph temperature versus vapor pressure, what we need to do is we need to do some calculations. We need to calculate we need to calculate 1 over the temperature. So we go through and calculate that. And then we also need to calculate the natural log of the vapor pressure. So we'd have to take the natural log of 0.8 and write that down, the natural log of 4.5, etc. And so we're going to get 2 sets of data, and then you have to graph the data. You graph the data, you get the line slope. The slope of the line is equal to negative heat of vaporization over R. R is 8.314, and so you can solve for delta H. I won't make you do that on an exam. Okay. Could be in the homework, though. Any questions? We can also express the Clausius-Clapeyron equation as in a 2-point form. This is something we will possibly do on an exam. This is useful for predicting vapor pressure at a specific temperature, provided you know the heat of vaporization and the boiling point. So here you need to know the heat of vaporization. But that's been determined by other people. It's all tabulated, and we can look those things up. So the 2-point form, the natural log of P2 over P1 equals this slope again, minus delta H over R, and then the difference between the 2 temperatures, T2 and T1. The thing I have the hardest time with here is remembering which is 1 and which is 2 for the pressures and the temperatures. But it's P2 over P1, and just like all of our delta things, it's T2 minus T1. So this could show up on an exam. Propane has a normal boiling point of minus 42 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. What's the vapor pressure of propane at 25 degrees Celsius? So this is going to use the 2-point form of the Clausius-Clapeyron equation. Come on. So the natural log of P2 over P1 is equal to negative delta H vap over R times 1 over T2 minus 1 over T1. We know that the heat of vaporization is this. We've got a normal boiling point, and we have this temperature. So we're given 2 temperatures, and we're asked for a pressure, but we don't have another pressure. Did you have a question?
So that the heat of vaporization is specific to that
Substance.
Yeah, that substance at that temperature.
Yeah, the heat of vaporization does depend a little bit on temperature.
Because it's the energy for 1 mole of substance
to vaporize at that particular temperature. So this is not the most accurate way to predict vapor pressure, but it's easy and convenient, and it gets us close enough, which a lot of times is good enough, right? Like we saw with water, the heat of vaporization at the boiling point is 40.7, and at room temperature it's 44. So it's different, but it's just a little bit different, right? It's not like one's 40 and one is 0.5 or something. That would be a problem. So here we are looking at 2 significantly different temperatures. And so this heat of vaporization, it might be right for one and not very right for the other, or it might be kind of right for both of them. We just have to go with it. So we need to decide which one is 1 and which one is 2. And you can do this to make things more difficult for yourself or easier for yourself. So I'm going to look at the pressures here and think, well, if I want to solve for a pressure, it would be easier to solve for P2, right? Be easier to solve for P2. So I'm going to choose P2 to be the vapor pressure that I'm trying to find, so that makes 25 T2. This is T2, and this vapor pressure is P2, just because I think it might be easier. If I start doing it and realize, oh gosh, that was the wrong choice, I could just start over and change the assignments. 1 and 2 are just different. They're not first or last or anything like that. So then this one is going to be T1. What's P1? What does normal boiling point mean? Why isn't it just boiling point?
Standard pressure.
It's at 1 atmosphere of pressure. Normal boiling point means at normal atmospheric pressure at 1 atmosphere. So the word normal tells me that P1 is 1 atmosphere. That is probably the most overlooked thing that happens to students on an exam. They get started on this and they're like, but I don't have P1. Normal means 1 atmosphere. We do have to be careful about units, okay? So let's just start out here. We're going to say natural log. P2 is what we're trying to find. And let's put in P1 as 1 atmosphere. Now let's think about these units. Does it matter what pressure unit we use here? We've got a ratio. As long as they're both the same pressure unit, it's okay, because the units are going to cancel out. So if I'm putting in P1 in atmospheres, then when I solve this for P2, the answer will be in atmospheres. I could convert this to torr and then end up with my answer in torr. It doesn't actually matter that much. So then minus delta H vaporization. Okay, so let's put that in here. That's minus 19.04 kilojoules per mole. And then I need R. Well, we had two values for the ideal gas constant. One was in liter atmospheres per mole Kelvin, and the other was in joules per Kelvin, mole Kelvin. I want to use the joules per mole Kelvin one. And that will be given to you on an exam, 8.314 joules per mole Kelvin. Because I've got joules here, right? No, I'm lost on my slides. 8.314 joules per mole Kelvin. Now, is that going to work out with the units? Close, but not quite, right? I've got kilojoules up here, and I've got joules down there. So I should make them the same, because I want the joules to cancel out. So what I could do is I could say, well, this, I'm going to take the kilo off here, and instead of writing kilo, I'm going to write what kilo means, which is times 10 to the third joules per mole. Or you could convert it separately and then write it in. Not proper scientific notation, but your calculator will understand. Times 1 over T2. What unit do I need for the temperatures? Kelvin. Because the ideal gas constant has kelvins. So 25 degrees Celsius, 25.0 would be 298.15 Kelvin. So 298.15 Kelvin minus. The real reason we want Kelvin here is because we don't want to end up with negative temperatures. It messes everything up. And then minus 42. So that's 273.15 minus 42.0. 231.15 Kelvin. Any questions? So this side is all numbers, right? So we can find out what that equals. Got negative 19.04 times 10 to the third divided by 8.314 times the quantity 1 divided by 298.15 minus 1 divided by 231.15, close parentheses, equals 2.226399.086. What are the units on that number?
Joules per.
Well, joules and joules cancel out, right? And the moles cancel out, and the kelvins cancel out. There's no units on it. So I have the natural log of P2 over 1 is equal to this. This is why I chose to put P1 as the 1 atmosphere. Because what's P2 divided by 1? P2. So we've got the natural log of P2 is equal to 2.226399. We don't really need all those digits. When we deal with logarithms, concepts of significant figures can get a little wonky. This is not one where I would try to trick you with significant figures. So let's just use a bunch of those digits. How do we solve for P2? We can't divide by natural logarithm because it isn't a multiplying function. We have to do the anti-log. So just like 10 to the x is the anti-base 10 log, e to the x is the anti-natural log. So P2 then equals e raised to the 2.226399086. So that comes out to 9.2664. And what's the unit on that? What? How did I get 9.2664?
Yeah. What is the e? Is that like
E is e to the x. So there's e to the x and there's 10 to the x. And they should be on the same button. This is the opposite of natural log, and this is the opposite of base 10 log. Okay. Yeah.
This is an ATM, correct?
It's in ATM, yeah. This is in atmospheres because of the unit that we used here. If I had used torr, then this would be in torr. Because whatever unit I use in the denominator, it has to be the same as the unit in the numerator. So that's going to be in atmospheres. And, we could argue about how many significant figures that should have. I think keeping too many is always better than not keeping enough. Because, if you round this down to just 2 and you do e to the 2, that's 7.38. That's a big difference in pressure. Like 2 atmospheres different. So better to keep too many than not enough. Any questions? So this equation could definitely show up, and any permutation where I give you 3 variables, or you should know 3 variables, and you have to find the other. We're going to try to finish this section. The critical point. So what happens if we vaporize a liquid in a sealed container, but we're heating it? So we don't just let it sit there and vaporize and come to equilibrium, but we're heating it in a closed container. Well, as the temperature goes up, the pressure's going to go up, right? Because you're going to get more and more gas particles, the pressure goes up. The gas is going to become more dense, the liquid is going to become less dense, and at some magical point, they're going to merge and become what's called a supercritical fluid. So here we're peering into a chamber. You can't get great pictures of this because it involves high pressures. So here we've got this little porthole into the container, and we see the liquid and the gas, and we increase the temperature, and the liquid is becoming less dense, the gas is becoming more dense, and at some point we get a supercritical fluid. The meniscus disappears. It's not a gas, but it's not really a liquid either. It's kind of somewhere in between, but it's one state. The temperature at which this happens is called the critical temperature. If you get above the critical temperature, then you have one state instead of two. So TC, critical temperature, is the temperature at which a supercritical fluid forms. You can't have a liquid above the supercritical temperature. The pressure that occurs at that transition is called the supercritical pressure. Supercritical fluids are very useful solvents. They use supercritical CO2 to decaffeinate coffee. So you want to get the caffeine out of coffee. I know, why would you want to do that? Some people can't handle it. So you want to get the caffeine out, but you don't want to take out all the stuff that makes coffee taste good. See, I would just give me the caffeine from the decaffeinated coffee. You take all the flavory stuff that I don't like. That would work out really well. I should do that. Supercritical fluid is used because the caffeine will be soluble in the supercritical CO2. And so you can pull the caffeine out. The other substances are not soluble in the CO2, and so they stay. And you move this off, move the caffeine away, and then you open the container, and what happens to that fluid that you were using? It goes away, because it's just CO2, which is in the air anyway, and you exhale it all the time. It's not toxic in reasonable doses, so it's not leaving any residues behind on your coffee, right? So, win-win situation there.